Hello everyone, welcome back to PW English Medium channel and welcome back to UMEED NEET English series. Friends, as you know, in this series we are completing each and every chapter of class 11th and 12th specifically for NEET 2025 exam. In these one-shot lectures, we are going to cover theoretical parts as well as PYQs from the last years, also some of very most important questions, right? So stick with me, stay till end of this chapter, because trust me, if you're going to attend this current electricity lecture, you're going to need no more lecture, right? Because I'm going to give you all the important notes, all the important derivations, all the important formulas, each of the things from this class. Alright, so without any delay, let's first look at the topics that we are going to do in today's class. Obviously, we are going to start with current. Then the most important part of the first section of this chapter is current, density, drift velocity, and along with this, we are going to also talk about Ohm's law and all the relations, right? And then we are going to discuss numericals also regarding that. Then another part of the lecture is now the numerical portion starts. That is battery and EMF, KCL, KVL, combination of resistors, power and Joule's law, and instruments. So even if you think that there might be one or two more topics, we are going to cover all of those things. Like for example, is dependence of resistance on temperature. I have not written it over here, but surely we are going to cover each and everything, not going to miss a single topic, right? So let's start today's class. Let's start with what we were talking about. Let's start with current, and let me give you a little bit of a brief revision, whatever you have been learning till current electricity. See, class 12 started with electrostatics. Is that correct? In electrostatics, we basically said that charge is not going to move. Charge will remain at rest, right? This was the fundamental principle. This was the fundamental principle of electrostatics, that the charge was at rest, and we discussed Coulomb's force and all of those things that you have done in chapter 1 and chapter 2. Now, when we are going to talk about current electricity, we are going to say the rate of flow of charge. We are going to start our chapter with this thing, that the rate of flow of charge, rate of flow of charge is current. A very easy peasy definition, dosto, right? A rate of flow of charge is known as current. Now you can say, sir, okay, that means that let's suppose if we have got a conductor over here, if we have got a wire, and please, from the very start, whenever we are going to talk about a wire, it's going to be a metallic cylinder. Is that clear? It's going to be a metallic cylinder, and we will say that let's suppose that we have got some charges over here. We have got some charges over here, and if they starts to flow in a direction, we say that the wire has got current, the material has got some current, right? And then we are going to talk about all of the other aspects also, so don't worry. Now the first question is that why do charges move, right? Why do charges move? Why do charges flow? What makes these charges move from one place to another place? So the answer for that is potential difference. Let's suppose that this side is positive, is having positive potential, this side is having a negative potential, right? So because of potential difference, charges moves. And now the next thing comes, what do we really mean by charges, sir? What are the charges over here in a metallic conductor? See, when we are going to talk about a metallic conductor, let's suppose we are discussing metals, the charges because of which we are saying that there is current are known as charge carriers. So don't get confused. When we'll say that what are charge carriers in metals or in metallic conductors or in wires, we mean to ask what are those charge particles which are flowing, because of which we are stating that there is current. So those things are known as charge carriers. In metals, we know that we have got loose electrons in the outer shells, right? You know all of these things better than me. So we have got electrons which are actually loosely bound, and these electrons will have a tendency to move towards the positive potential. So this is how the electrons are going to move. So in this direction, there will be flow of electrons. Is that clear? So we have till now we have studied that rate of flow of charge is going to be known as current. That means I can define current as I equals to, and see, whenever something like this comes up, whenever something like this comes up, that is rate, we define two types of formula. One is average current. So average current is going to be called as the number of charges flown in a unit time between, let's say, 2 points. These are the 2 points, right? Between 2 points. Or if I would have said that, okay, let's talk about the instantaneous current. So instantaneous current will be written as limit delta t tends to 0 del q by del t. All right. Don't have to worry about this. Is nothing but dq by dt. Please don't ever panic whenever you see something like this. This is nothing. This is your easy peasy derivative of charge with respect to time. That's what we are talking about. You have done this numerous of times. You have studied that velocity can be written as rate of change of displacement with respect to time. Is that clear? So you differentiate the equation of displacement with respect to time and you get velocity. Similarly, if you have got an equation of charge as a function of time t, and if you are going to differentiate it, you are going to get current. So alright, so this is quite easy for all of you. Now, what are the different things regarding current? Obviously, I can see that the SI unit of current is going to be coulomb per second, or known as ampere. Now, current is actually a fundamental quantity. Current is a fundamental physical quantity, and ampere is a fundamental unit. Okay, so whenever someone is going to ask you what is the dimensional formula of current, obviously you know it. It's going to be M0 L0 T0 and A1. So it's a fundamental quantity and has got fundamental unit, right? Now let's quickly move on. Hopefully now you are with me. We are on the same page. We have talked about what do we mean by current. Why current is basically rate of flow of charges. Charges can be different in different types of mediums. Like for example, as we were talking about metals. So in metals, the charges were electrons, and the direction of flow of electron is something like this, and the direction of current will be opposite to the flow of electron. This is by convention. Okay, you must be knowing this, that this is the direction of current, which is, it should be opposite to that of flow of electrons, flow of electrons or negative charges, right? Not going to bore you all with all of those things that electrons have the mobility, protons cannot move. You know all of those things, right? There is going to be no current because of protons, unless and until there is a hypothetical question. I mean, anyone can frame a hypothetical question saying that we have got like 100 protons moving, but generally speaking, we'll always have electrons, and if electrons are moving in a particular direction of current is going to be opposite of that. That's it. Now, if someone is talking about an electrolytic cell, right? Surely we can talk about an electrolytic cell. Let's suppose you have got a positive electrode, you have got a negative electrode, and then you have got an electrolytic solution over here. Then we have got both the things. We have got both ions. We have got positive and negative ions. Is that clear? We have got positive and negative ions, and these are going to be your charge carriers. These are the charge carriers in the case for an electrolyte. So it's not like, if someone is going to ask you what are charge carriers, it's not like always electrons are going to be charge carriers. Electrons are charge carriers in the case of a metal. When we are going to talk about an electrolytic cell, charge carriers are going to be what? Charge carriers are going to be both positive and negative ions. Hopefully everything is clear, right? Now if someone asks you, what about, sir, if I want to find out the flow of if I want to the amount of charge flown. So let's suppose we want to know the amount of charge flown. So now this is very easy. as I've told you, that current can be written as I'm talking about the instantaneous current, it can be written as dq by dt. So the charge flown can be actually written as integral of dq. Further, we can rewrite it as I times dt, and let's suppose they are talking about from time t1 to t2. That's it, right? So this is going to be the way by which you can actually find out the charge flown between two time interval. Hopefully everything is clear till this point. Current is really simple. Always remember that current is actually a scalar quantity, right? So it is a scalar quantity, although we do talk about its direction, but when we talk about direction, we really mean to talk about the direction between the direction in a circuit, right? We really don't mean to say that, okay, if we are talking about if the direction is going to change, we are not going to say that it becomes a different we are not going to treat it as a different physical quantity like we used to do it in velocities or any other vector quantity. Also, there are some reasons behind it. Sometimes, most of the time, you are going to see that because current doesn't follow the vector addition, but it's not it is not the absolutely correct answer for that, but surely current is actually a scalar quantity, right? And also, please don't get into all of those tensor and tensor kinds of things. That's also absolutely wrong explanation. Now let's move on. Let's talk about a vector quantity, right? So that we can really understand why current is actually a scalar quantity. Let's discuss what do we really mean by current density. We can define current density as it is the current per unit normal area. It is the current per unit normal area. Now, definition is very easy. Let's understand it by a diagram. Let's suppose we have got a wire, and this wire has got, let's suppose this has got a cross sectional area of A, right? This area is A, and let's suppose I am saying that the current flowing through this wire is actually I, right? Now, no matter what happens with this, with the shape of this wire, the current will always remain same. This is the main part. So let's suppose even after some time, let's suppose the wire turns out to be something like this, or it moves something like this. At all points, the current will be same, that is 1 ampere only, or sorry, I ampere only. I have not used any number over here, but it's going to remain same. Why is that? Because current is rate of flow of charges. The number of charges which are passing through this point will be exactly equals to the number of charges passing through this point per second, and same for this point as well. Why we are saying that? Because we are not assuming that I mean, you reason me out. Why would the number of charges will change? Number of charges will change only because either you are going to increase the number of charges. We are not doing that. Either someone is going to take some charges out of the wire. Neither this is happening, right? So we are going to say that the current remains the same. Now what we are saying is, let's suppose initially, I mean, if you are going to closely look at this area, let's look at this area. This has area A. Now, hopefully till now every one of you know that yes sir, area is actually a vector quantity, and if area is actually a vector quantity, we are going to say something like, sir, this is actually the vector quantity, that is A, right? So I'm going to say, okay, so that means for this particular part, current density will become J1. I'm talking about J1 will become current I divided by per unit area, that is A. Is that clear? Hopefully this is clear. Now let's talk about some another area. Let's not say that we are drawing the same type of area now. Let's say I have tilted this by an angle theta, something like this, right? And that angle is, let's suppose, this angle is theta, by which actually I have tilted it. So this angle is, let's suppose this is theta. Alright. Now can you tell me this whole thing now, this whole of this surface has got now area A. Now if I am going to ask you, what is the current per unit normal area? Now area is not A, area is going to change. Why? Because now we are going to take the component of this area and that will actually become, this will actually become something like this, and this area will be A cos theta. Hopefully you are getting it, right? Absolutely. I mean, this is the area about through which current is actually passing, something like this. Is it clear? So now I'm going to actually define current density as J equals to and J is a vector quantity, current upon area vector, or I can write current as the dot product of two vector quantities, and hence we can say that current is a scalar quantity, right? Again, let's not waste a lot of time on talking about vector and scalar over here. But still, this is a way better explanation than just saying that current doesn't follow the vector law of vector addition. All right. Also, if you are going to talk about the magnitude of J, so magnitude of J can be written as I upon A cos theta. Same thing. I mean, now you won't find it surprising if I'll write that it is a vector quantity. The SI unit of this one is going to be ampere per meter square, and I'm not going to waste time writing its dimensional formula. You're smart enough to write it down, right? But still, the diagram is through this diagram you can clearly understand what do we really mean by current density and what is its relation with current, right? Now let's move on. Hopefully everything is clear now. Now what I want us to understand is, when we are going to talk about materials, like when we are going to talk about different types of material, we are going to categorize materials into three types that you have been doing through since the junior classes. That we have got conductors, we have got semiconductors, and we have got insulators. Now we actually define them in such a way that we talk about the order of free electrons density. All right, so the order of free electrons density, we have got density over here in conductors is actually 10 to the power 28 per meter cube. So this is actually number of electrons in number of electrons per unit volume, right? Whereas in semiconductor this drops to 10 to the power 16. All right, and for insulator it would be way smaller than the semiconductor as well, but still it's an important, and that's what I was saying. If you're going to stick with me till the end of this lecture, you are going to get many such important notes, and these notes are, it is important for you to, like for example, as NTA might give you a match the column and they might throw some data over there, right? Obviously they'll never ask you this question in MCQ. I mean in your normal MCQ questions, but they can ask anything in match the column, right? Now let's solve some questions also. Let's solve some questions till what we have studied. Question says the current I in a conductor is expressed as I equals to 3t square. By the way, this is a PYQ. This is a PYQ question, not from NEET but from JEE mains. Achha, if we are studying for NEET, why are we talking about JEE mains? Two reasons. I'm repeatedly saying to my students who are studying from me that if you want to prepare really good for your NEET 2025 along with NEET previous year questions, please also solve JEE mains previous year questions. Why is that? Because first of all, the difficulty level is we can say it is approximately same Also, we are expecting most of the faculties and we are expecting that NEET 2025 must be slightly difficult than the past year, and which will be on our side. I mean, this is something which will be good for us, right? So if that happens now, it is good for us to solve some PYQs from JEE mains as well. Now let's see what this question is talking about. The current in a conductor is expressed as I equals to 3t square plus 4t cube. All right, where I is in ampere, T is in second, the amount of electric charge that flows from a section of a conductor during this time. See, we know that this thing can be actually written as dq by dt. And if someone is asking you about dq, I'm going to just say that let's just integrate it. And if I'm going to quickly integrate it, can I quickly do it? If I'm going to quickly integrate it, this will become 3t cube by 3 plus 4t raised to the power 4 by 4. And since they are talking about the two limits, I'm going to just put from 1 to 2, right? 3 can be cancelled out, 4 can be cancelled out, and this will become cube of 2 plus 1 raised to the power 4 minus, then I have got cube of 1 and plus I have got 1 raised to the power 4, right? So definitely this thing can be cancelled out by anything. So this will be nothing but 8, and this is minus 1, that is going to be your 7 coulombs. So the answer for this question is going to be 7 coulomb. Now please understand that this is the same level that you can also expect in JEE mains. Sorry, NEET 2025, right? Now let's quickly understand over here. They have given us current, we just integrated it, this becomes 3t cube by 3, this was become 4t raised to the power 4 by 4. Now from lower limit 1 to 2, we have just put 2 raised to the power 3, that is 8, and 1 raised to the power 4, then minus, then lower limit. Hopefully everything is clear till this point. Now let's move on to the next one. Also, I'll try to give you some homeworks as well. Please write down those answers in the chat box, right? The next question says the electric current through the wire varies with time as I equals to I naught plus beta t, where I naught is 20 ampere and beta is 3 ampere per second. The amount of charge flown through this in 20 seconds is. Can I give this question in homework? Can you do it? Similarly over here as well, I am going to write charge as the integration of I naught is 20, so this becomes 20 plus beta is actually 3, so it becomes 3t, and from 0 to 20, right? So they have not talked about the lower limit, so it will be 0. So 0 to 20, right? Whatever the answer is, please write down in the chat box. And by the way, this is dt over here. So this is going to be 20t plus 3t square by 2. That's it, whatever it's going to be. Doesn't matter, from 0 to 20. Again, this is from previous year JEE mains, right? Easy peasy questions, friends. Now let's move on to the next one. This question is saying, now this is not from previous year. This question is saying current passing through a wire decreases linearly. Decreases linearly basically means if someone is going to ask you to draw its graph, this will look something like this. Let's say we have got current over here, we have got time over here, although we don't have to draw a graph for it, just for your sake, just for the sake for understanding. So they are saying that it linearly decreases from 20 to 0. So let's suppose at t equals to 0, it was 20 ampere, and at t equals to what? In 4 seconds, this drops to 0. They are saying that what is the total charge? The reason also for drawing me this diagram was that if you will find out the area under the IT curve, right? So area under the IT curve, area under the IT curve will give you the charge, isn't it? And why not? Because the thing is that charge is actually the integration of I dot dt. So integration means area under the curve, right? So this would basically mean that if you have got the graph for the curve for charge and time, the slope will give you the current. Very easy peasy thing, doston. All of these things you have been studying since mathematical tools. So we are not talking about anything new. So the area of this is going to be, that's also going to be the charge, is going to be half base times height, so that's going to be 40 coulombs. Everything is SI unit. Good. You tell me everything's fine till now. I mean, under 25 minutes we have completed the basic part of this the basic part of the first portion. Now let's talk about that is something that is called as drift velocity, right? Because it's a one shot video, I'm going to straight away dive into what drift velocity is. Obviously, then going to explain each aspect of it. See, the drift velocity can be actually defined as it is the average velocity of electrons, average velocity in electrons in presence of or I'll simply say average velocity of electrons when electric field is applied. When electric field is applied, right? What are we talking about? Let's see. The thing is, let's suppose that we have got a metal over here. We have got a metallic surface over here. And let's talk about two cases. The two cases are, the first case is A, when there is no electric field. When there is no electric field, and if there is no electric field, that means there is no potential difference. Obviously, we have got many electrons over here, those free electrons, right? And both of these things are kept at room temperature, around 300 Kelvin. Both of them are kept at room temperature. Now, at room temperature also, these electrons have some velocity, right? And you can find out that velocity, by the way, you can find out that velocity using your half mv square equals to 3 by 2 kt by that formula that you have learned in kTg, right? For a single electron, of course. So you can find out that velocity, and that velocity is of really high order. So over here, these electrons are moving quite fast. These electrons are moving actually quite fast and in complete random direction. In complete random direction. Well, you can surely ask me, why are they moving? The reason is because of thermal agitation. They are kept at room temperature. They have got certain energy because of the energy they are gaining, because of thermal energy gaining from room temperature. And because there is no electric field, they are not moving in any particular direction. They are not flowing in any particular direction. They are just drifting, and they are colliding with another electrons or with another fixed positive ions, right? So this is what happening at room temperature. One more thing, that the order of these the average speed of these electron is going to be of 10 to the power 5 meter per second. That means quite high, right? They are moving quite fast. But what will happen if I'll apply some electric field over here? So let's suppose that I give some positive potential to this side and some negative potential to this side. Now let's suppose an electron was initially moving in this direction. So the initial path was something like this. Obviously, I'm not saying that it would have moved in a very straight path. It would have collided with any other particle, but at this point the initial velocity was in this direction, right? Now what's going to happen, because we have applied an electric field, and by the way, electric field is in this direction from positive to negative. We have applied an electric field. What's going to happen is that a force will act. So this is the B part where we have applied an electric field. So a force will get applied on an electron, and that force will be actually minus E times E. That means the charge of an electron times the electric field that we have applied. Further, we can rewrite that. So that means it will also have an acceleration. Nothing so difficult about it, right? And if it has got acceleration, by the way, in which direction the force will act? So on electron, the force will act on in this direction, and by the way, on each and every electron, the force will act on this direction only. So this is the direction of force, right? So it was moving, it was about to move in this direction, but because of this force, it will start to actually move in this direction. So this is going to be the direction of electron because of electric field. Now obviously it will not move because it will now collide with any other particle after some time. And so the similar thing will happen with every other electron. So every other electron which was, let's suppose an electron was moving in straight direction from the very start. So it will accelerate, and it will get accelerated, and it will strike with some another particle. So in a way, every electron will start to drift in a particular direction, right? So it's not a very harmonic motion, or a very what we can say a streamlined motion that we see, like for example, if this pen is moving like this, that's not how electrons moves, right? Electrons move something like this, that they move, then they collide, and then they transfer their energy, and then some another electrons, obviously all the other electrons are moving in a particular direction, right? So I mean, if I am going to apply some basic kinematics over here, the basic kinematics over here, let's suppose I am applying a basic kinematics for one of the electrons. So I am going to say that, let's suppose its initial velocity was u1. That means when there was no electric field, it experiences an acceleration of a, and it collides after a time t1 with any other particle, right? So the thing is, the speed with which, the velocity with which it gets collided is written by v1. Similarly, I can write it for many other particles. So v2 can be written as u2 plus, acceleration is going to be same, and t2. Now please tell me, what is t2? T2 is not the mean time. T2 is the time for which the second electron traveled, and T2 was the time after which second electron got collided. So there are like number of electrons similar to this. So we can rewrite it for like n number of particles. So straight away let's write for nth particle. So it's going to be written as un plus an times tn. Now let's do a very simple mathematical operation, and that is, let's add them and take average of it, right? So if I'm going to add all of these things, and I'm going to also take an average of it, so that's what the drift velocity is, average velocity of all the electrons when electric field is applied. So that is what I'm going to write, v1 plus v2 and so on, vn whole divided by the total number of particles, that is n, equals to u1 plus u2 plus un and whole divided by n, plus acceleration is common, right? And obviously I don't have to write this an over here. Acceleration is same, so I'll take a as common, and I'll write t1 plus t2 and so on plus tn whole raised to the power n. Hopefully everything is clear till this point. Please have a look. After this, let me write it somewhere else. Let me write it over here on the new page. I'm going to just say that if this is the case, can I write v1 plus v2 plus v3 as drift velocity vd equals to acceleration can be written as just minus e by m, and t1 plus t2 plus t3, the average of all the time, can be now written as relaxation time tau. So you must have seen this formula, so that's why I've directly written it. So over here, tau is going to be called as the relaxation time. That is the mean time between two collisions, or average time between two successive collision. All right, hopefully everything is clear. Now from this you can have actually like mini questions. There can be mini questions developed from this particular formula, that is Vd is equals to minus EE tau by m, right? So now the first thing that we are going to do after this is, after drift velocity, we are going to actually derive, we are going to actually state Ohm's law, then we'll try to prove Ohm's law using all of this formula, right? But first of all, let's have a look what will happen if I'll increase the temperature, right? So if I'll increase the temperature, frequency of collision will increase. So temperature is actually directly proportional to frequency of collision. And if frequency of collision will increase, this would mean that tau will decrease. Is that clear? It's quite logical. If more number of collisions taking place in a given time, that means the average time for collision is going down. So if temperature increases, tau actually decreases. So this is a very important relation. Please remember it. After this, my dear friends, we are going to say, also please note this thing, that Vd is actually quite less. This is actually really small. Right? Really small. If you remember, when there was no electric field, the average velocity was of the order of 10 to the power 5. This is going to be in 10 to the power minus 3, minus 4, something like that. Now, next, let's move on. And let's talk about relation between current and current density. Now, the relation between these things comes out to be, see, current is nothing but total charge flown divided by total time t. Now, let's just suppose that we have got a conductor. Let's suppose we have got a conductor, something like this, having length L, area of cross section A. So this has area A, length L, right? And there is also one more thing, that is small n, which is actually number of electrons per meter cube. Number of electrons per meter cube. So del Q will be actually written as the total charge. So what is the total charge? So one electron has got charge E. And how many electrons are there? So in 1 meter cube there is n number of charges. And how much of volume is there? So the volume is actually A into L divided by, what is the dt? So delta t is basically the time taken by an electron. So let's just say, because we have already defined what drift velocity is, I'm going to just take an electron, I'm going to say its drift velocity is Vd. So the time is going to be just L by Vd. So L can get cancelled out. So the relation comes out to be NEA Vd. So a very important relation, please remember it. NEA Vd. Alright, where n is the number of electrons per meter cube. Now we have got two things. We have got two formulas. One is drift velocity can be written as EE. By the way, I am just writing the magnitude, EE tau by m. Another formula is I equals to NEA Vd. So can I put, instead of Vd, can I put EE tau by m? So I would get I equals to NE square A tau by m, and instead of electric field, my dear friends, electric field would be, if electron is moving in this direction, this would be positive potential, this would be negative potential. So the potential difference between these 2 points can be actually written as, E into L, isn't it? Right? Because I am assuming that electric field is uniform. So E into L, so that means E can be written as V by L. So this thing can be written as V by L. Now please understand, we can rearrange all of this thing and we can rewrite this thing as V equals to M into L divided by NE square tau into A. Have a look at it. Have a close look at it. And see, that's what I was saying. I know that this is a one-shot lecture. We can actually skip derivations, but we'll not call this as a derivation. Why? Because this is just plugging the value of Vd into I, then plugging the value of E in terms of V, and that's it, right? So V is the potential difference, and all I can say, obviously I should write current also. So current over here. Now if you will closely see, for a given wire, what I'll say is, I'll write it over here. For a given wire, M, L, N, E, tau and A are all constant, isn't it? I mean, if I've got this wire, I've already taken this wire, its length is not going to change, area is not going to change, N is the number of electrons per meter cube. It is a property of the material, that is not going to change, right? Tau is the relaxation time. Now you can say that sir, tau can change, right? So that's why if you remember, even in grade 10th we used to say under same physical condition. So when we are talking about tau, right? So we must also state that this happens at same temperature. So there's a caveat to it, there is the temperature should be same, right? So that's why we say that under same temperature, under same physical condition, under constant physical condition, we will say that potential difference is directly proportional to current, because everything else is a constant. And now the proportionality constant over here is actually nothing but R. So in this case, resistance will be actually equals to ML divided by NE square tau times A. So this is the value of resistance. Have a look. Almost derived it, isn't it? Hopefully everything's clear till this point. ML NE square tau times A. What is resistance? Resistance is the property of a material to offer hindrance to the flow of current, right? Acha, also we know that when we'll talk about resistance, resistance depends upon, it directly depends upon the length, inversely depends upon the area. Through this, we can say that resistance can be written as something that is called as resistivity times length into area. So resistivity is nothing but resistivity. How you are going to define resistivity? See, resistivity is the resistance of the material having unit length and unit cross-sectional area. So again, equating the formula, resistivity will come out to be, rho will come out to be M upon NE square times tau. Alright. So now let's again come back. If you are going to say what will happen if you are going to actually increase the temperature. So we are going to actually divide it into two parts. If you are going to talk about conductors, for a conductor, if you are going to increase temperature, that will actually decrease relaxation time, that we have already talked about, right? So if you are going to increase temperature, that will decrease tau, and that will increase resistivity, right? So tau is also I'm going to write also, tau is inversely proportional to resistivity. So this means that is resistivity directly depends upon temperature for a conductor, for all of those metals that you have talked about. So in layman terms, if you are going to increase the temperature, a good conductor will move towards becoming a bad conductor. Its resistivity will increase, so will its resistance. Is that clear? Hopefully everything is clear. So that was about conductors. In semiconductors, something different will happen. See, I'm not saying that in semiconductors this is not true. Still, this statement will hold true. Still, in semiconductor, temperature is actually inversely proportional to relaxation time. But along with this factor, there is also one more factor. That is, with increase in temperature, the number of free electrons per unit volume increases. Now, please don't get confused that, sir, just now you said that N is not going to change. I was talking about conductors. In semiconductors, N is the number of free electrons. So in semiconductor, what happens is, I'm just briefly explaining it to you. You'll learn it in detail in semiconductors band theory. What happens in semiconductor is, when you are going to increase the temperature, more number of electrons will be able to actually jump the energy gap, and they will be able to take part in the conduction, right? So the number of electrons will change. So because of this, and by the way, this factor actually overpowers the other, right? So this factor overpowers the other. So we are going to say, okay, so two things is happening. With increase in temperature, tau is actually decreasing and N is increasing. Is that clear? So if in the denominator N is increasing and this factor is overpowering the another one, so we are going to say, okay, we are going to say that, okay, the denominator actually increases, so that means the resistivity will decrease. So in short, we are going to say that with increase in temperature, resistivity will decrease. So simply going to write it something like this: resistivity decreases with increase in temperature for a semiconductor. See, in one page I have explained you many things. Now this is going to be really important for you if you want to. I mean, you're going to see many questions from this one single page, right? And by the way, this is nothing but your Ohm's law and proof of Ohm's law. Everything is being done. Now let's move on, and let's move to. Acha, one more note over here. A very simple thing. I've already written it. This is actually, if I've got this is something that is called as non-uniform cross section, non-uniform, a wire which has got non-uniform area. As we can see that A2 is greater than A1. So if A2 is greater than A1, what we'll say? We'll say that drift velocity at J1 will be greater at J2. Drift velocity will be greater than at this point. Also, drift velocity and also current density will be greater at A1. Why we are talking about drift velocity, by the way? Everyone knows, obviously, sir, if area is less, current density will be more, because current density is current per unit normal area. If you are going to decrease the area, current density will increase. But what is happening with with drift velocity? See, whenever you are going to see some questions like this, it would be even better if I'll say that a constant current is flowing through it. This is actually important. If constant current is flowing, so I'll write it over here that I is constant. So if I'm going to say something like current is constant, I'm going to say that current is written as NEA VD. Now because current is constant, NE is, no matter, it will remain constant. That means the product of A and VD is constant. This means that VD is also inversely dependent on area. But again, we have got a condition for it. Current should be constant. Current is not going to be constant, then you will use the formula of E tau by M. This is a very important thing, okay? So this is for constant current. If someone is going to talk about for constant potential difference, please use something like VD equals to E tau by M. So that means it is independent of area, right? So in this particular case, VD is independent of area, as you can see. Hopefully everything is clear till this point. Now let's move on and let's see some more curves. First one is linear VI curve that we often see, right? Now see, even if at really high temperatures, na, like for example, if this is at low potential, but at really high voltages, let's say this is I, this is V, something like this can also happen. Something like this thing can also happen, right? So this is a non-linear behavior. Also, you can have non-linear behavior of semiconductors. So in case for semiconductors, you will have something like, let's say this is actually, now over here I'll write current over here. It's in milliampere. You'll learn all of these things in detail in semiconductor. This is microampere, and this is how it's going to be. All right. That part is forward bias, this is this is reverse bias. By the way, I'm going to talk about something like this. Even at these points, Ohm's law is applicable at individual points. All right, at individual points, Ohm's law is still applicable. So don't think like, okay, Ohm's law is not following over here. Ohm's law, this is ohmic devices which follow Ohm's law for a particular range. This is not ohmic devices because V is not directly proportional to I. But at these individual points, you can still find out the value of resistance, because you can find out the value of R by taking the slope. So now let's move on to something that is known as temperature dependence of resistance. We have already seen, yes sir, if you are going to increase the temperature, see what till now what we have seen. We have seen that if you are going to actually increase the temperature, resistance will increase for conductors. For conductors, that means all the metals. If you're going to increase the temperature, resistance will decrease for all these semiconductors, right? This is what we have studied till now. Now the thing is, let's just write a mathematical equations for it so that we can solve some problems. Now there is no requirement of derivation over here. The thing is, I mean, you have seen this formula many times before also. The formula is look something like this. So rho equals to rho naught times, acha, by the way, first we can rewrite it for resistance. Resistance equals to R naught times 1 plus alpha into delta T, or rho equals to rho naught times 1 plus alpha into delta T. So these are the two formulas. Rho naught is the resistivity at initial temperature. At initial temperature, let's say that's T1. This is at T2. That would mean delta T is nothing but T2 minus T1. And the unit of alpha is going to be, what's going to be the unit of alpha? If you closely see, I can rewrite this thing as alpha, rho minus rho naught. Is that clear? Rho minus rho naught divided by rho naught times delta T is equals to alpha. So this is the formula for alpha. I have done nothing but I have multiplied rho naught with this bracket, and I've written alpha as something like this. Now, if you will closely see, this is actually nothing but ohm meter. This is ohm meter. So alpha's unit will come out to be per degree Celsius or per Kelvin. And you don't have to worry about units over here, right? Because alpha, Kelvin and Celsius are linear scales. So you will not face any trouble. So you don't have to worry about conversions. Okay. Now let's move on. Let's look at some of the questions over here. Before that, also have a look at what happens with change in temperature. This is a copper. Copper basically means we are talking about conductors. So for conductors, if you're going to increase the temperature, this is some order of like 50 Kelvin, then 100 Kelvin and so on. At 0 Kelvin, obviously resistivity will be 0, but as you're going to increase, by the way, see, I am also explaining you the order of resistivity. So order of resistivity for a metal like copper is around 10 to the power minus 8 ohm meter. When you're going to talk about nichrome, which is an alloy, it goes to micro ohm meter, right? And can you please see over here that with increase in temperature, it's showing a very what we can say a positive relation with change in temperature. As temperature is increasing, resistivity is also increasing. What we are seeing over here is with increase in temperature, resistivity is increasing, but that increase is actually quite small. So if you want to use a particular material which doesn't show a very close what we can say a very sensitive relation with temperature, you should use nichrome, because with increase in temperature, nichrome's resistivity will not increase that much. This is what we are going to call as semiconductor. Acha, this will actually also explain one thing. If we have talked about this alpha, what does it tells us? This tells us that for conductors and for all the metals, alpha is going to be positive. Because if you are increasing temperature, delta T is positive always, we are increasing it, that's how we call it. Delta T is positive and rho is greater than rho naught, that means alpha will be positive. So for conductors, alpha will be positive. But for semiconductors, we say that if temperature increases, resistivity decreases. So temperature increases, delta T is positive, but rho is less than rho naught, that means alpha will be negative. So for semiconductors, alpha will be negative. So again, you have got two more points and all of these are very, very important. Done. Hopefully everything is clear till this point. Now let's move on and let's have a look at some questions. Now I think it's a good time, you should pause this video, take a look, solve it by yourself and then unpause it, right? Question says a current I flows through a uniform wire of diameter d when the electron drift velocity is v. The same current will flow. Now can you please check, they are talking about that the same current will flow through a wire of diameter d by 2. That means if they have said that the same current is flowing and they want us to find out drift velocity at another point, use the equation of I. I equals to NEAVD. Right? So because same current is flowing, so we are going to simply write NEA. By the way, with area it means NE pi d square times drift velocity is v, right? Drift velocity is v, and this will be also equals to NEA, so pi d square by 4, because now it becomes d by 2 times vd dash, new drift velocity. Ne pi can be cancelled out, d square can be cancelled out. Hopefully everything is clear, right? So vd dash will become 4v. So D is going to be the correct answer. Have a look. Quickly, let's move. Hopefully everything is clear. Moving on to the next one. Have a look. This is for you. This is for homework. Very easy. Non-uniform drift speed. Just now we have did it. Right? So it is quite easy for us to now understand, because drift velocity also depends inversely upon area. So that means Vp will be greater than Vq. See. Let's move. Next question is saying the resistance of a platinum wire, platinum resistance thermometer at the ice point. All right. So what do you mean by ice point? So ice point is nothing but 0 degree Celsius. And steam point is 100 degree Celsius. Steam point is 100 degree Celsius. Are 8 ohm and 10 ohm. So that means resistance at 0 degree Celsius is 8 ohm. And resistance at 10 degree Celsius is, at 100 degree Celsius is 10 ohm. And we have to find it at 400 degree Celsius. So what I'll suggest you to do it always for questions like this, you can find out what alpha is now easily. Take the reference as 0 degree Celsius. That will help you. So I'll simply use this equation that R is equals to R naught into 1 plus alpha into delta T. So I'm going to write R equals to, so I'm going to first take these two things. So 10 equals to 8 times 1 plus alpha into 2. What I have done, I have taken 0 degree Celsius to be my initial temperature and final temperature as 100 degree Celsius. So sorry, final temperature as 100 degree Celsius. So this is going to be 100 change in temperature. So final temperature, final resistance is 10. Initial resistance is 8, 1 plus alpha that I need to find out times 100, right? Times 100 is the change in temperature. From this I can find out what alpha is going to be. So this is actually, it's going to be, see 10 minus 8, that is 2 equals to alpha into 800. So alpha will come out to be 1 upon 400 per degree Celsius. You can rewrite this thing as something like this. Done. So we have got what alpha is. Now let's apply. Now let's take these two and let's write resistance at 400 degree Celsius is equal to, again I'm taking the reference at temperature 0 degree Celsius. That's why I have marked it down. So this is will be 8 1 plus alpha times change in temperature now is 400. So this gets cancelled out and this will be actually, this will be 2, this will be 16. So the answer should be 16 ohm, option B. Have a look. Hopefully you have paused it. Please try it by yourself. Anyway, I'm going to do it. Then you can unpause and you can check your answer. Please quickly see. Now moving on to the next question. Please have a look. Read it. The question says two wires A and B are made up of the same material. Same material would mean that they have got same resistivity. Alright. And have same mass. Alright. So we are going to use this fact also. So they have got same mass. Wire A has radius 2 millimeter. Wire B has radius 4 millimeter. The resistance of wire B is 2 ohm. The resistance of wire A is. Question is quite simple. Why they are saying that they have got same mass? The reason is that, see, we know that mass can be actually written as, density is mass upon volume. So mass can be written as density into volume, right? If they are saying that their mass is same, their density is also going to be same, that means their volume is same. Please understand that volume of A will be actually equals to volume of B. Because they have got same mass, they are made up of same material. So same material means same resistivity and density. Right? So if volume is same, we are going to say that area, that is pi R1 square times L1 equals to pi R2 square into L2. Pi can get cancelled out. After this, they are saying that radius is 2 millimeter. So this is actually 2 millimeter. I am just going to simply write 2, not going to change unit. What about length? Are they talking anything about length? Two wires A and B made up of same material having same mass. Wire radius is this, radius is this. So L1 equals to R2 is 4 millimeter and this is L2. So this would basically mean I can cancel out one of the 4 with this. So that means L1 is actually equals to 4 times of L2. Alright. And they are also saying resistance of B is actually 2 ohm. So resistance of B is actually equals to 2 ohm. This would mean rho into L. So L is L2 divided by A2. So A2 is going to be pi R2 square. Right. So this is actually equals to 2. So I mean, if we are going to find out RA, that will be rho. Instead of L1, can I write 4 times of L2? Right? And if you'll also closely see, R1 is also equals to half of R2, right? So R2 can be written as double of R1. So instead of R1, can I also write it as half of R2? So this would mean pi R2 square times 4. So this would mean 16 times of rho L2 divided by pi R2 square. So this would mean 16 times 2, that is 32. So 32 should be your answer. For this particular case, 32 should be your answer. You can do it more quickly. It's up to you, right? So now let's move on to the next question. Before moving on, let me give you one more note over here. You might have also seen questions like stretching of the wire, right? Whenever a question comes in which they talk about stretching of wire. So stretching basically means that the volume will remain constant. Volume will remain constant, right? So if volume will remain constant and they are saying that it has been stretched to n times of its original length. So let's suppose that initially the length was L and now we have stretched it. Now the length becomes n times of original length. So the resistance will become n square of the original resistance. This is something which you should be able to understand it. We can derive it definitely, because see, if we are saying that A1 times L1 is actually equals to A2 times L2. So let's say initial area is A, initial length is L, and now they are saying that length becomes n times. So this would become NL. So A2 would become A by N. And now the new resistance will become rho L, which is now n times divided by new area, which is A by N. So that's how we are going to get it becomes n square, right? So I've derived it for you, but you must remember it to save time. Similarly, if they are going to talk about that if it is stretched in such a way that the radius becomes 1 upon n times, now the resistance will become n to the power 4 times r. This is really important. If you are going to derive these things in NEET, it's going to cost you some time. So it is recommended that please just remember these things. All right. After this, my dear friends, we have got one more topic which is related with drift velocity and electric field, that is called as mobility, a very small topic. Mobility is actually defined as the drift velocity per unit electric field, and this is just, we are going to talk about its magnitudes. It is drift velocity per unit electric field. So if we'll substitute the value of drift velocity, it would be E tau by m and divided by E. So E can get cancelled out, so this will come out to be E tau by m. All right. So please understand that this will just talk about that drift velocity depends upon the charge, which I have just written as E, and depends upon the mass. So if you're going to talk about an example, if you're going to talk about a proton and an electron, right? So we know that mass of proton is greater than the mass of electron. So because of this, and they both have same charges, because of this, mobility of electron will be greater than that of mobility of proton. That's it, right? A simple example. Nothing to worry about. You can also define its unit very easily. Now let's come back to some important topic, which is actually battery and EMF, right? So we must have seen a battery, something like this. Let's suppose that we have got a battery over here. And it is connected with some load resistance. This thing is actually known as load resistance, the main electrical appliance for which we are using our battery. And also over here we have got some internal resistance. So let's say the EMF of the battery is E. That's what we are going to define right now also. And this is the load resistance. By the way, this battery or if the battery is actually combination of cells. If you are going to talk about a cell, let's look at an example of a cell. Let's suppose that you have got an electrolytic cell over here, a basic electrolytic cell, and you have got two electrodes, something like this. And then external circuit attached with this, and let's say this is positive electrode, this is negative electrode, right? That is anode and cathode, and current flows outside from the circuit something like this, and inside the circuit current flows from the negative, from the cathode to anode, right? Now the thing is, if we are going to say, if you are going to define what EMF is, so we are going to say that EMF is basically the potential difference between the terminals of the cell, This is one of the definition. Another definition can be also, it is the potential difference across the cell in an open circuit. You can also define it as the energy it gives to a unit charge to move through the complete circuit and through the cell, right? But these two definitions are going to do the job. Now the thing is, let's suppose that total current I is flowing in this circuit, right? And see, from this particular topic now, you must understand the concepts of potential drop, potential difference, and potential also. I'm going to use this concept. The main thing that we are going to use this battery and EMF is to understand what do we really mean by potential, potential difference, and potential drop, all of those things, right? Now please see here. If current is flowing from the battery, first of all, this thing is actually known as, when current comes out of the positive terminal of the battery and goes inside the negative terminal, this thing is actually known as discharging of battery. Next thing is, let's suppose that we are talking about the potential difference between these two electrodes is, let's say, 100 volt. So 100 volt becomes the EMF of the battery. Right? And now let's say that you ask me, sir, okay, does this means if I'm going to use an voltmeter, something like this, will this voltmeter give me a reading of 100 volt or a little less than that? So the answer is going to be, this voltmeter will not give you a reading of 100 volt. It will give you a reading a little less than that. The reason is, out of this 100 volt, there is also a potential drop at R. Now first let's understand what do we mean by potential drop, right? And even before that, let's understand why do we actually, what does electrical appliances use? If you have got a resistance something like this, and current I is flowing in this direction, and let's say current is 2 ampere and the resistance is of 5 ohm. Let's just take an example. All right, let's take an example. Now what does this mean? This basically means, let's say this is actually 2 ampere and this is 5 ohm, sorry, 5 ohm. First of all, as soon as you see the direction of the current, you know that, okay sir, this is the low potential, this is the high potential. all the electrical appliances, which means all the resistances, do not use current, they use potential difference, right? So there is going to be a potential drop when you are going to move from point, let's name this as point P to point Q. There is going to be a potential drop. Why? Because this device of resistance 5 ohm will consume a potential. What's going to be that potential? That potential will be found out using V equals to 2 into 5, that is 10 volt. That means these 2 points have a potential difference of 10 volt, which means that Vp minus Vq is actually equals to 10 volt. Now, I have no interest in finding out what is the potential of point P. What is the potential of point Q? I know that potential difference between these 2 points is 10 volt. Now I can imagine anything. I can say that let's suppose the potential of this point is actually 200 volt. So this would mean the potential of this one is 190 volt. That's it. I really don't know what this individual potential is. Are you getting it? So I can assume anything to solve my question. Or what I can usually what we do is we just say that, okay sir, let's suppose that this is actually, if this is 10 volt, then what will happen? So I'm going to say that, okay, so this will become 0 volt. That's it. Are you getting it? So the thing is, when you're going to talk about something like this, now let's discuss it. Let's for now, let me just remove this voltmeter from here, and let's say we are finding out the total resistance of this circuit. Now you know that, sir, total resistance of this circuit is hopefully you all know. By the way, I am also going to remove this diagram from here. All of you know that, sir, these two resistances are in series. Everyone knows this, na? Hopefully everyone knows कि हाँ sir, these two resistances are in series because same current is flowing through them. So if I want to find out the R equivalent would be R load resistance plus internal resistance. This would mean I would be actually equals to total EMF E divided by total resistance R plus small r. So if you want to know that what is going to be the reading of the voltmeter, then what you need to do is you need to do two things. Voltmeter will actually give you reading E, but out of E there will be a potential drop at R also, and that will be given as small I into R. This is something that is known as terminal potential difference. Now please understand. If you are going to talk about what is the potential difference between these 2 points, this point and this point. So let's name this thing as point, I'm going to name something else. So point A and point B. So VAB is actually known as terminal potential difference. All right, let's go step by step. Now that's why we were saying, if let's suppose we are talking about an open circuit. So open circuit basically means that there will be no current. So if there will be no current, I will be 0. So V will be actually equals to E. So it is the potential difference across the cell in an open circuit. But if you have got a circuit, if the current is flowing through it, then please, out of E there will be a small potential drop at small r also, right? And E minus IR is going to be called as terminal potential difference, which will be the reading across that voltmeter. So this is very important. All right, and out of that formula also you can rewrite E as V plus IR. V plus I into R. Exactly. And I've also explained you what I is going to be. I is going to be E divided by total resistance. Although right now I have not explained what series combination is, but I'm not expecting that any single one student will have a doubt in what series combination is. Right? You have already done that in grade 10th. Now from here, let's move. And let's talk something also about internal resistance. What happens, because this is actually list of 2 or 3 things which most of students actually miss, right? So I'm going to make a note over here. Please take a look on this. internal resistance directly depends upon the distance between the two electrodes. If you are going to increase the distance between two electrodes, ions will have to cross a larger distance, which will increase the internal resistance. Internal resistance is inversely dependent on the area of the dipped electrodes, right? Because if area is going to be larger, it will be easier for electrons to move, to actually get to the other electrode. Internal resistance is directly proportional to the concentration of ions. This is actually a little bit a slightly confusing thing, but still this is absolutely correct. The thing is that with increase in the ions, uh, uh, because of you can say because of clustering of the ions, it is difficult for them to move, or you can simply say that the mobility of the ions decreases, and it is also inversely proportional to temperature. If you are going to increase the temperature, they will have more kinetic energy, they'll move, their mobility will increase. So these are some of the 4 factors which are very important for internal resistance, right? Moving on, actually not very important but very ignored, that's what I can say. Chalo, acha, let's move on. Let's move on from here. And by the way, I've got one question for you in homework. I'm not going to explain it. Why? Because I have already explained many questions. The question is saying the resistance of a thin wire is 1 ohm at 20 degrees Celsius. So at 20 degrees Celsius, the resistance is of 1 ohm. The wire is placed in a liquid bath and its resistance rises to, so we don't know what this temperature is. Is that clear? What is the temperature of the bath? So we have to find out the temperature, and it increases to 1.2 ohm. What is the temperature? And they have given us that alpha is actually equals to 3.8 times 10 to the power minus 3 per degree Celsius. Do it by yourself. Write down the answer in the comment section. This is from slide number 26. Now let's move on and let's move to KCL and KVL. You know that this is actually very, very important. And before starting KCL and KVL, let me actually extend that topic of potential drop and all of those things. So before KCL and KVL, let me explain the sign conventions. And trust me, students who are right now watching this video, if you have got slight doubt in sign convention in KCL and KVL, everything will got cleared after this, right? Acha, by the way, KCL doesn't require sign convention. So let me explain what KCL is first. KCL, which also stands for Kirchhoff's current law or junction rule, basically says a very simple thing. It says that, let's suppose we have got a junction. So let's first define what a junction is. A junction is a point where 2 or more than 2 wires meet. So this is going to be called as a junction, right? This is going to be called as a junction. Now, at this junction, 2 things can happen. See, only 2 things can happen. Either a current will be incoming, that means either a current is going to be coming towards the junction. So let's take some example. Let's say some of the currents are coming towards it. So something like this, or current might also go out of it. Let's say this is I1, I2, I3, I4 and I5. So KCL basically states a very simple logic. KCL states that the summation of all the incoming current will be actually equals to the summation of all the outgoing current. And this is based on a very simple fact of conservation of charge. And trust me, we are going to use KCL quite often, right? More than KVL. Why? Because KVL, I'm not against of KVL, but KVL requires loops and writing equations, then finding out those equations, and you will see what I mean. By we are going to use more KCL than KVL. Okay, so this is a very simple thing, nothing else. I mean, what's so difficult about this, right? Now let's talk about the sign convention that we require in KVL. By the way, sign convention of what? This is an important question, right? Sign convention of what? Sign convention of reading potential differences. How you read and note down the potential differences. This is what we are talking about. So, when we are going to talk about change in potential difference, two things can happen. Either there can be a potential gain or there can be a potential loss. Potential gain or potential loss, or often known as potential drop. That is what potential difference basically means, right? Why sometimes we call it as potential gain? The thing is, whenever you are going to you read a potential gain, we are going to use it with a positive sign. Now again, this is not a law or something like that. This is just our convention. This is our belief. This is our way of writing it, right? Now, what do you mean by potential gain and potential rise? Let's suppose we are saying that we have got two resistors over here, and by the way, both of them are same. This is R, this is also R, this is point A, this is point B, this is point A, and this is point B, and current is moving like this, I, and current is moving like this, I. So what's the difference, sir? The difference is in the reading. Let's suppose we are, in the first case, we are reading it along the direction of the current. That's how I am explaining it to you, right? So whenever something like convention comes, it all becomes a game of how you understand it. So how I am explaining it to you, let's suppose that we are reading it in this direction. So this is the direction of our reading. Our reading of what, dosto? Potential difference. So we are going to read it something like this. Okay, VA, potential difference of A, we move. Then we know that, sir, wherever, if we are moving like this and current is in this direction and there is a resistance, this resistance will consume potential. It will consume, surely, sir, it will consume potential. So I'm going to write it as minus IR. I'm going to write it as minus I into R. This is the change in potential. So if I'm going to write the whole equation for you, I'm going to write it something like this. We are going to write VA minus IR and plus VB, whatever VB is, and then we again come back to that, the whole thing. So we write it equals to 0. What that equals to 0 is, I'll explain it. Don't worry about it. First of all, I just want you to know that, okay, sir, whenever there is going to be a potential drop, now we'll write it with a negative sign. That's all I want you to know. So the reading is going to be minus IR. Or what you can also rewrite this thing as that VB minus VA is actually equals to minus IR. What will happen if we'll go something like this? If this is going to be a reading. So we know that VB, now VB minus VA, sorry, we are going to write something like plus I into R. Just like that. First of all, you understand this thing. So wherever there is going to be a potential gain, we write it with a positive sign. Wherever there is going to be a potential drop, we are going to write it with a negative sign. Now let's come back to KVL, and I'll explain how to write those VA and VB, all of those things. First of all, what does KVL means? KVL says that the sum of change in potential, in a closed loop, is 0. And this is based on conservation of energy. If there are potential drops, there are going to be somewhere potential gain. These things will add up and it will always be equals to 0, right? So algebraic sum of all the change in potential difference across a closed loop is going to be 0. All right. Next, let's assume we have got a loop over here. So let's say this is E1, R1, E2, R2, E3, R3, and this is R4, and current that is flowing is I in this direction. I have just assumed a loop that I have just made, right? Nothing special about this loop. Let me also name some points. Let me name some points as A, B, C, and D. Now, according to this rule, if I'm going to assume a loop, so first of all, you need to assume a loop. What do you mean by loop, sir? Let's assume that we have got a loop like, applying KVL across loop A, B, C, D, and let's come back to point A. So loop gets completed. Acha, how we are writing it, also we can decide it in which way we want to move. So I have decided to move in this way, like in anti-clockwise. You could do it in different way also. And let's say we have started our journey from point A. So we have started our journey from point A, current is I. So if current is I, current I will pass through this point. Current I passes through R4. Current is moving from A to B, and you are also reading the change in potential from A to B. That's what I was talking about. So you are moving along the direction of current. So there is a potential drop. So write this thing as, so this is applying KVL at loop ABCD. Let's write this thing as minus I into R4. Now let's again move. This is a positive potential and negative potential. So from positive to negative, that means potential drop. So we are going to write again minus E4. This was, sorry, E3. Then again we are moving in this direction and another resistance comes. Again there will be a potential drop. So minus I into R3. Then again we move, there is another resistance I into R2. Then negative to positive potential gain, that means minus E2. Then we move in this direction, minus I R1, and then again plus E1. When you again go back to the same point, you equate it to 0. That's how you write the equation. Hopefully it is clear to you. Now you can make any number of loops, anything. This is the thing. Please remember that sign convention is something that we have defined for ourselves. You can find completely different. Like for example, if I multiply this whole equation with minus sign, it will not change anything. Na? It is mathematically absolutely correct. So after this, let's now solve one or two questions, like for example as something like this. Now solving by KVL is your homework. Solve KVL by homework, because I want you to learn the quickest way. Now to solve these problems, and see, in these problems you have got a very easy thing. That easy thing is that this thing is actually known as a clean wire. Can you please see, this whole wire is actually clean. Why? Because it has got no battery and no resistance. That means whatever potential difference, whatever, I am not talking about potential difference, I am saying whatever potential is of this point, same is going to be of this point and same is going to be of this point. Of course, you can ask why. The answer is going to be potential difference is there. There is potential difference because of either a resistance, an appliance or a resistance can change the potential because it will use it, or a battery, and we have neither of them over here. So let's suppose that this point has 0 volt potential difference. Now this is where I was talking about that we are going to assume some things, right? So let's suppose that this has got 0 volt, so this will also have 0 volt, this will also have 0 volt. Acha, let's say the potential difference of this point, potential of this point is x volt. I can assume it, na? I can assume that potential is of x volt. Next thing that I am assuming is, lots of assumption, next thing that I am assuming is, let's say current I1 is flowing like this, current I2 is flowing like this, and current I3 is flowing like this. I1, I2 and I3. So this is also an assumption that all the currents are actually outgoing. So according to KCL, that's why I was saying that we are going to use KCL. According to KCL, summation of outgoing current I1 plus I2 plus I3 will be equals to summation of incoming current, and there is no incoming current, so this will be equals to 0. Next point, I1 can be written as potential difference. Any current can be written as potential difference upon resistance. So I1 can be written as potential difference is X. Now how you read it? You move, this is X, you move from positive terminal to negative. So that means X minus 5 divided by resistance, that is 2, plus X minus 10 divided by 2 plus X minus 20 divided by 2 is equals to 0. Can we find out what X is going to be? So this will be 3X minus 35 equals to 0. So X will come out to be 35 by 3. Now whatever this is going to be, just put the values of X over here on these three individual terms. That means if you want to find out I1 would be just 35 by 3 minus 5 whole divided by 2. Sorry for this. Hopefully everything is clear, right? Come on. So now what I want is, I want you to find out what I2 is going to be and I3 is going to be, right? Can we use the same logic over here? Please have a look. Please pause this video and do it by yourself. Now if you will see this one, and if you will try to use the same logic, you will face one difficulty, and that difficulty is that there is no resistance in the first arm of this circuit, right? So no problem, still we can see that I mean this is a complete clean wire, right? So what I'm going to do is, I'm going to say that fine, let's say all of these points have 0 volt potential, 0 volt, and let's choose this point to be our junction. Let's say this point has got X volt potential, and out of this X, let's say I2 current is going like this, I3 current is going like this. Let's suppose two things. This is I1, I2 and I3. And then again let's suppose that this point has got some potential Y. And from this point, let's say I4 current is going like this and I5 current is going like this. So this is I4 and I5. Have a look. We have now used 2 points over here. So for junction X, that means at point G, I'm going to say that I1 plus I2 plus I3 is equals to 0. Now I don't know what I1 is, right? I don't know what I1 is. So what I'm going to do is I'm going to keep this I1 as it is. I'm going to write I2 as X plus 30 divided by 1 plus I3, I'll write I3 as Y minus X. Why I've written something like this? Because I know if I have assumed the direction of I3 to be this, I know that Y will be at higher potential, right? So Y minus X divided by, just a second. Can we do anything else than this? Is there any other way for this one? Let's check, because we don't have any resistance that is given in I3 also, right? So we'll have to use another way. All right, no worries. Let's do one thing. Let's not write it as X. Let's use another method. Till now we have done two things. We have rightly assumed that these points have potential 0 volt, right? Okay. Also, this has no resistance. That means if this is 0 potential, I must assume this thing to be 10 volt. Is that clear? Right? We have correct. I mean, there is nothing wrong in assuming these as at 0 potential. So if this point is at 0 potential and there is no resistance in this branch, that means this will be at 10 volt. And now again, this is a clean wire. So this means that this will be at 10 volt. This will be at 10 volt. This will be at 10 volt. Now let's read current for each branch. For example, and let's leave this branch for now because I don't have resistance for it. So wherever you are not going to have a resistance now, let's solve it at last. It will automatically, you are going to automatically find it out. Let's solve for BG. Let's find out current at BG branch. What are we looking at? This point is at 10 volt. Now let's read the potential. 10, and there is a potential gain of 30 volt. So at BG, I'll write it as 10 plus 40 divided by the resistance, that is 1, that is 40 ampere. 40 ampere in which direction? From B to G. From G to B. So I have found out one current which is 40 ampere in this direction. Done. Let's do the same thing for the other ones as well. Like for example as FC. The point is at 10 volt. Then we move from positive plate to negative plate. And potential drop is of 40. So minus 40 divided by resistance is of 2 ohm. That means minus 15 ampere. Minus 15 ampere basically means one thing. We were moving like this. And if you are getting minus 15, that means current is moving in the opposite direction. So the current is going to be something like this. And this is going to be 15 ampere. This means this is actually current is from, I'll write it as 15 ampere from C to F. Then last part, ED. So ED was 10 minus 50 divided by 2. That means you are going to get again minus 20 ampere or 20 ampere from D to E. So that means this current is 20 ampere. Now please understand, you had 4 branches, you got current in 3. Now the next thing is 20 plus 15 is going to add up. Why? Because this is incoming current, they will add up at this point. So 35 ampere of current will flow through this wire. And 40 ampere of current is going in this branch. This means that the last branch must have a current of 5 ampere in this direction. So that's how you are going to get each and every current, because 5 plus 35 will be equals to 40 ampere, right? So KCL is going to help you a lot. Else what you would have done is you would have used KVL, which will take a lot of time. So please make a note of it. Now one question in homework, by the way, this is an easy one. Again, you can assume these points to be at 0 volt. Right, this point to be at X, and I1, I2, I3 and I4, and solve it, right? And write down the answer in the comment section. Now let's move to some other question which deals with the combination of resistance. Now I know I haven't taught combination of resistance, but there is no need for it. You have already done in grade 10th. Let's straight away jump to some questions, some good questions. Now if you are going to see, again over here I am going to talk about the same thing. If this is a point, this point is also going to be A. And because again I have got a clean wire, this point will also be A. If this point is B, this point will also be B. Now you have got only 2 points, and when resistances are connected between same points, that means they have got same potential, which means we are talking about a parallel combination. Alright, so you have got 2 points A and B. This is R, R and R. So the R equivalent is going to be R by 3. Very easy question. Let's start with some easy, then let's move. Now see, you are going to also get some special circuits, something like this, right? The special thing about this circuit is that you can actually draw some line of symmetries over here. For example, as one of the line of symmetry that can be drawn is something like this, that is passing through from point 3, 4 and 5, right? So this is your line of symmetry. So if this is the case, also this is also a line of symmetry. If this is the case, the point at which these two things are meeting, now you can actually do something like this. You can actually detach these points. And I'll give a reason to you, reason for this. What you can actually assume is, let's suppose that a current I is flowing from this direction. Let's say that a current of 2I was flowing in this direction. Equal part of resistance is in the downward direction, equal part of resistance is in the upward direction. So equal current will distribute. So I and I, right? Similarly at this point also same thing will happen, and at this point also same thing will happen. Is that clear? When you are going to reach at this point, there will be no sense for current to move towards the upward direction. Why? Because they both are at same potential. So the current will not move. So what you can do is you can actually break the circuit from this point. Now how the circuit will look like, These two resistance will be in series. These two resistances will be in series, and we are going to get something like, so this is going to be R, and these will become R and R 2R, R and R 2R, and please understand these branches will be in parallel, so that will again be R. So R, and then you have got again R resistance over here, and similarly you will have similar thing in the downward also. So you have got R, R, and one more resistance R, something like this. So this is going to be a simpler circuit. Hopefully you are getting it. All right, same thing over here as well. See, if you want to find out the resistance between point A and D, do similar kind of thing. Let's suppose current I flows from this part, current moves, then current will also get redistributed along this path. Now please try to understand one thing. If let's suppose current I is moving like this, right? And at this point current will distribute in this direction and in this direction. Can you please check which are the points which are at same potential so that we can remove them? Please understand. If I'm going to say that this value of current is actually I, and I've got a 2 ohm over here and I've got 1 ohm over here, I'm going to just assume that let's say this is I1 current and this is I2 current. I2 current is flowing, again there will be a potential, there will be a distribution of current at this point. Hopefully everything is clear till this point. Acha, also current was moving from here, so current will also get distributed over here as well. So over here also current I will pass. Then again there will be a distribution. So a current will move in this direction and a current should move in this direction. So that means this resistance is of no use. You can remove this resistance. B and C will be at same potential. Similarly, this point will be of no use. This will be at same potential. Please understand quickly. So now to solve these problems in a similar way, what we are going to do is we are going to write point A over here. And we know that from point A equal current will distribute, right? And point B and C are at same potential. So let's just mark point B and C something like this. B comma C, and let's mark two resistors from A to B and A to C, and there is no reason to draw the resistance between point B and C because they are at same potential. Now similarly from B to C, let's mark another point E comma F. So from B to E and from C to F. So again R and again R. Now from E and F, we have got another point at D. So last point at D, so that will be again R and again R. Now you can easily find it out. All of these resistance are in parallel, so that will be R by 2 and times 3. So that will be 3R by 2. So 3R by 2 is going to be the answer. Alright, so that's how you can do problems like this. Now let's move on. Let's move to another question, something like this. The question is saying the value of unknown resistance X for which the potential difference between point B and D will be 0. Now please have a look at this. If someone is saying to you that we have got a structure like this, we have got a structure like this, and we have got some resistances over here, R1, let's say R1, R2, R3 and R4, and someone is saying that the potential of this point is equals to the potential of this point, this means that they are talking about balanced Wheatstone bridge, because this is the condition for balanced Wheatstone bridge, isn't it? Because this is the only condition at which there will be no current flowing through this branch, through this arm. If I'll connect a galvanometer over here, it will show a zero deflection. Why? Because galvanometer reads current and there will be no current because potential difference is same. And if this is the case, the condition is actually R1 upon R2, sorry, R1 upon R3 is actually equals to R2 upon R4. So this is the condition for galvanometer, so for balanced Wheatstone bridge. So in this case, we can see that this is 12 and 12. So this is going to be 24. 24 and 24 will again become 12. So that means R1 is actually equals to 12. This is 12 and 12. So this will become 6. So this one is actually equals to X plus 6. R4 is actually 0.5. This is 1 and 1. So this is also 0.5. That means this ratio is coming out to be 1. So this would mean that 12 upon X plus 6 should also be equals to 1. This means that X should be equals to 6. By the way, this was also from past year JEE mains. Now let's move to another topic of combination of cells. The topic is really easy, not to worry about anything. We are going to talk about two types of combinations of cells over here. First is series combination. Now in series combination, we say, let's suppose we have got many cells connected, like for example as E1, E2, E3 and so on, and a load resistance R is also connected with them. So this is E1, E2, E3, E4, R1, R2, R3, R4. First of all, what I have done in this diagram is I have correctly connected them. What do you mean by correctly connected? That each positive terminal is connected with negative terminal. This is known as correctly connected. So in this case, E net will become the sum of EMFs of each one of them. So E1 plus E2 plus E3 plus E4. And R equivalent will be just the series combination of internal resistances R1 plus R2 plus R3 plus R4. So if someone tells you to find out the value of current, current would be E equivalent divided by capital R plus small r equivalent. Now that's what I was saying, nothing really different about this. The only thing is, if someone says let's suppose that if n identical cells are connected, if n identical cells are connected, are correctly connected, then E net will come out to be NE and R equivalent will come out to be N into small r, right? And if any one of them is wrongly connected, you will decrease the net EMF by 2, right, by 2E. Next is parallel combination. So you think about it, if you have got something like this, if this is one of the branch, let's say you have got E1, E2 and E3, or for let's suppose that first we have got all the batteries have got same internal resistance, same EMF, same internal resistance, and you have got a load resistance over here. So this is also E, R, E, R, E and R. Now think about it. What we mean to say in parallel combination is replace all of these cells with a single cell, right? And this is an R equivalent. So that single cell will also have, E net will also have the same EMF as E, and all the R equivalent, all the resistances will be in parallel combination, that means R by N. So current will be actually equals to E divided by R by N plus load resistance. That's it. Hopefully this is clear to you, right? Now what will happen if someone says that they are not of same EMF? Then you will have to use different formula. If someone says that, okay, this is, let's suppose this is E1, R1, E2, R2, E3, R3, something like this. So in this case, we are going to assume that, okay, fine, let's say this is current I1, I2, I3, and this is current I. So I1, I2, I3, and I. So this is the total current I. Now again, I am going to say the same thing. Let's suppose we mean to find out, this one is going to be I1 plus I2 plus I3 and equals to V. I was saying that again we'll use KCL. I1 plus I2 plus I3 is actually equals to I. Now if you will closely see how I can actually write current is, what is the potential difference between this point? So potential difference between this point is actually E1 minus I1 into R1. Please understand, this is the terminal potential difference between these 2 points, and it will be same across each one of them, isn't it? Please tell me. So can I write E1 minus I1 R1 is equals to I into R? Wouldn't it be correct if I'll write something like this? Because by terminal potential difference, I mean to say this potential. It will be same all across all branches because they all are in parallel. So the terminal potential difference between this branch is actually equals to E1 minus IR1. Hopefully everything is clear till this point. So if this is the case, I can rewrite this thing as E1 minus IR divided by R1 equals to I1. Please have a look. So can I similarly write E2 minus IR upon R2 is equals to I2, and E3 minus I into R divided by R3 equals to I3. Please have a look. That's it. We'll add them up. Substituting the values over here, we'll get E1 upon R1 plus E2 upon R2 plus E3 upon R3, and I'll take minus I as common, minus IR as common, and we'll be left with 1 upon R1 plus 1 upon R2 plus 1 upon R3 and equals to total current, that is I. Hopefully this is clear, right? Now after this, what we are going to do over here is, by the way, please understand that I have added all of these things up. Now the next thing is going to be, let's transpose that to the other side. So this will become something like this. So I'll take I as common, and that will become 1 plus R times 1 upon R1 plus 1 upon R2 plus 1 upon R3 equals to E1 upon R1 plus E2 upon R2 plus E3 upon R3. So current will finally come out to be E1 upon R1 plus E2 upon R2 plus E3 upon R3, and divided by, you will have 1 plus R times 1 upon R1 plus 1 upon R2 plus 1 upon R3. So this is the this is for if the cells have different EMF. If they have got same EMF, then that was really easy. Now if someone says if we have got n number of cells, so the formula will become I equals to, if you have got n number of cells, the formula will become summation of EI divided by RI whole divided by 1 plus capital R summation of 1 upon Ri. This is going to be your formula. Hopefully everything is clear till this point. Now let's move on. Let's move to some more questions and some more concept. Electrical power. Any power is actually the rate at which work has been done. Rate of doing work. But because we will have to define it in terms of current electricity, we will define something like rate at which energy is consumed or produced. So power is going to be just dV by dt, right? And we know that dV can be actually written as V dq, so that would be V dq by dt. Or then you can have different formulas like P equals to Vi or V square by R or I square into R. These are all different set of formulas just for power. Now why do we use these formulas? Where do we use them? A very important thing, that is something that is called as rated power and rated potential. Rated power and rated potential. There is also something called as rated current, but usually we are going to see something like this. Rated power and rated potential. Now the concept is very simple. Rated power and rated potential basically means that if you have got a bulb, being manufactured at an industry, it is manufactured to work at a certain potential. That potential is known as rated potential. And the power that it will consume at this potential is known as rated power. So using these two information, what you can actually do is you can find out the value of resistance. Because the thing is, understand one thing, that what they are going to do is they are going to say that, let's suppose, and we are going to look at one question also, they will say a bulb which has got rated potential as 220 volt and rated power as 100 watt is being used at a potential of 50 volt. What is going to be the power consumed? So first, whatever the information you have got from this, find out the value of resistance, because that will not change. So resistance will come out to be VR square by PR. This will not change. Now again that they have given us the potential, you can find out the new power. Similar to this, see, this was the question from JEE mains, I think 2023 or I think 2024. They have said it is rated at 50 watt to 200 volt, and now you have to find it out at 100 volt. So just use this information to find out the value of resistance. So resistance will be actually equals to VR square divided by PR. So this is going to be 200 times 200 whole divided by PR is 50 watt. So this will become 4. So this would become 8000 ohm. Now use this to find the power at this thing. So this will become again 100 times 100 and divided by 8000. So that would be 5 divided by 4 or 0.2. Sorry, that would be I think everything's good till this point. Can we please check? So this was actually 800, not 8000, 800. So that would be 12.5 something. This is actually 800, right? So this is going to be square of 100 divided by 800. This. All right. So you can actually expect some questions like this in NEET as well. Now let's move on and let's move to some another question, something like this. Like for example, they can ask you to grade the bulb in order of their brightness. So if we have to do this. See, the thing is, current is same in all of them. Whatever current is flowing in B1, same current will flow in B2 and same current will flow in B3. Is that clear? So current is same. So I know that I've got another formulas also, like I've got V square by R, but I use I square times R because current is same. So if current is same, power will be directly proportional to resistance, right? And resistance is actually equals to PR square by VR. And if you will closely see, VR is also same all across it. 220 volt, 220 volt, 220 volt. So this means that resistance is directly proportional to PR in this specific case. Please understand. Resistance is directly proportional to the square of PR in this specific case because obviously rated potential is same. So the bulb which has got the highest P rated power will glow the brightest. Is that clear? Quickly write down in the chat box. Sorry, this is a recorded session, but quickly write down if you have any doubt in the comment section, right? So with this information, we'll simply say that power which has got highest resistance will glow the brightest, and that means B1 will glow the brightest, then comes B2 and then comes B3. If similar question comes in parallel combination, then the answer would change, right? Then the answer would change because then we are going to say that now the power that is consumed is inversely proportional to resistance. Then I am not going to use this formula because in parallel combination I know that potential is same. Now let's move to the next topic, which is maximum power theorem. Now what do we mean by maximum power theorem? This basically says, let's suppose we have got a load resistance at R and we have got a battery with an internal resistance small r. We want to find out the value of capital R in such a way that this capital R consumes the maximum power. And see, all we need to do is we need to actually just find dP by dR and equate it to 0. Right? And how are you going to do it? See, we know that current can be actually written as nothing but E divided by R plus R. Also one more thing, power is nothing but I square R. Power is nothing but I square times R. So just substitute the value of current. If we'll substitute the value of current, we'll get the answer as small r equals to capital R. Alright. So if you are going to substitute, if you are going to first put the value of this, so this would basically means d by dr, and this would be E square times R divided by R plus R square, and you'll have to actually equate it to 0. So you'll see that capital R comes out to be small r. So this is the thing that you need to remember. We are not differentiating it. You can do it very easy. You just have to apply normal quotient rule. That's it. All right. So this was the maximum power theorem. Now the last topic, that is the instruments. In instruments, we use galvanometer. First of all, understand what galvanometer is. We'll learn the principle and working of the galvanometer in magnetism, because it works on a principle which we are going to learn in magnetism. But still, galvanometer right now, till now, we can actually understand that galvanometer is actually a device which measures small current. It measures small current like milliampere, microampere, and a very sensitive device. All right. So the thing is that we are going to do two types of conversions from galvanometer. We are going to convert it into ammeter, and we are going to convert it into voltmeter. Now, since it is a very sensitive device, we must always, now this is something that I'm explaining it to you so that you can understand it, how to actually solve the problems. Let's suppose we have got a galvanometer, something like this. All right. In reality, it would look somewhat like this. You must have seen in your schools. Right. Now, something that is known as full scale deflection. Full scale deflection means the maximum amount of current a device can measure. So, always remember, because galvanometer is a very sensitive device, we must always save our galvanometer. So, this is something that is called as Ig. Ig is full scale deflection current. We never want, let's suppose the full scale deflection value for a galvanometer is, let's suppose 10 milliampere. Now we would never want a 5 ampere current to pass through that galvanometer. What will happen? Galvanometer will actually get spoiled. It will not work. It will wiring might get destroyed, right? So because of all of those reasons, galvanometer, we are seeing galvanometer is a very sensitive device. Now the next thing is, galvanometer has also got some resistance G. Now if you want to convert it into, first let's say if you want to convert it into ammeter, right? So let's first understand the conversion of ammeter. Now what till now what we have learnt, we must save our galvanometer. This is one of the thing. We want to convert a galvanometer into ammeter. So we have got a galvanometer something like this. We are going to connect a very low resistance wire, that is also called as shunt, in parallel. Please understand, for many students who actually try to learn ammeter first time, they think, sir, but ammeter is connected in series. Why are you connecting it in parallel? Two different things. First of all, this whole thing is actually known as an ammeter. All right. So the thing that you see as an ammeter is this thing. This thing is actually known as ammeter. And this entire thing is connected in series, not the shunt, right? So shunt is actually, now you know that ammeter is used to actually measure current. So whatever the current that you want to measure, let's suppose you want to measure 10 ampere, 15 ampere, something like this. So that large value of current is coming from here, right? Now if you would have connected that shunt in series, what will happen? That 10 ampere of current will pass through your galvanometer and galvanometer will stop working. It is not meant to measure that much current. Is that clear? So what we do is, we use a very low resistance wire over there. Why? Because current will choose the less resistive path. So now what will happen is, major current will pass through this shunt, and a lesser value of Ig will pass through this galvanometer. So this current will be Ig, and the remaining current will pass through, that is I minus Ig, through that shunt. So I am going to write an equation like this, that Ig times the value of resistance of galvanometer is actually equals to I minus Ig times the value of shunt, right? So this is the equation. I am not writing any formula like this. Question can ask anything. and you can find out the value now. Obviously, we'll solve some questions. If they'll talk about voltmeter, now we connect a high resistance wire. Now we don't call it as shunt, it's a normal wire. We connect that with series with galvanometer, and this whole thing is actually known as a voltmeter. And this thing is connected in parallel. Alright, and by the way, now apply the same logic and understand it. So usually this is of high resistance. That's why they say that ideally ammeter has zero resistance, and ideally voltmeter has got infinite resistance. So if this is the case, we are going to simply write that V will be actually equals to Ig, because now the current that will pass through this is going to be Ig times G plus R. Now let's look at one of the example. Let's look at this question. They are saying a galvanometer of resistance 100 ohm, so capital G is of 100 ohm, is connected in series with a 400 ohm, measures a voltage up to 10 volt. Alright. So resistance is of 10 volt, sorry, resistance is of 400 ohm, and it measures voltage up to 10 volt. What we can do from this information, we can find out what Ig is going to be. Then they are saying the value of resistance required to convert the galvanometer into an ammeter. So let's first find out Ig. So from here I am going to write 10 volt is actually equals to Ig times 500. So Ig will come out to be 1 by 50, right? 1 by 50. Now they are saying that let's convert it into so that it reads 10 ampere. Now please understand, 10 ampere of current should come from here to a galvanometer whose full scale deflection is actually only 1 by 50. And this is the value of shunt that we want to find out. So that's it. We are going to just write 1 by 50 multiplied by the value of G, that is 100, will be actually equals to 10 minus 1 by 50 times the value of S. Now what's going to happen is, if you are going to closely see, this will be written as 1 by 50, obviously 1 by 50 can be actually written as 0.02. Is that clear? 0.02. So in front of 10, can I ignore 0.02? I think I can. So I'll ignore it. So this will become 2. So shunt will be actually, the value of shunt will be, hopefully everything is clear till this point, the value of shunt will be actually 1 by 5. Just a second, let's have a look. Acha, they are talking about finding the value of X, na? So we have found out 1 by 5. So let's multiply 2 zeros over here. So I think it's going to be 20, right? So that the answer should be 20. Hopefully you have got it. In one question I have explained voltmeter and ammeter both. Is it clear? Quickly tell me in the chat box, comment box. Do one question in homework of galvanometer. A galvanometer has a resistance of 50 ohm that allows a maximum current. See, galvanometer has a resistance of 50 ohm and Ig is of 5 milliampere. It can be converted into a voltmeter to measure 100 volts. So 100 volt would be actually equals to Ig times G plus R. Very, very easy here. Very, very easy. Just find it out. Okay. Next, 3 voltmeters all having same different internal resistance are joined as shown in the, when the same potential difference is applied across A and B. They are very easy. This is from JEE mains past year, right? So that's why I've kept it. See, V1 plus V2 will be actually equals to V3. That's it. Because these two are in V1 plus V2 will be actually equals to V3. Those two branches are in series combination, parallel combination. Last question, and in homework, a galvanometer having a resistance of 10 ohm shows a full deflection. So galvanometer has 10 ohm and it shows a full scale deflection of Ig is given as 3 milliampere. Please, that the thing that I told you to ignore the value, na, please remember that whenever you have got like a value like 10 and something like 0.001, ignore that 0.001, you will get to the correct answer. And we want to find out the value of we want to measure 8 ampere, so, and find out the value of shunt. Very easy, do it, write down the answer in the comment section. Alright, so that will be all, my dear friends. Other than this, we are going to also come back with some more questions series. In that, we'll solve some more questions which we were not able to solve in this class, right? So thank you so much. If you have any more suggestions, please write down in the comment section. I'll be back with another one shot lecture for UMEED NEET series. Till then, take care. Thanks so much. Bye bye.